Come back to this. Now we will resume this with this. Now we already mentioned the welded, bolted. Oh, sorry, my bad. It's time to start going back and look at the double angle connection with this time bolted. So if you have bolts on both sides, that means we generally have to consider only big four and bearing tear out. So that's it. No more to talk about really, because when you don't have the welds on this side, you have bolts, or bolts without eccentricity should be straightforward. Maybe the small difference would be that instead of that picture, you now have something that looks like this perhaps. Okay, and now you have bolt holes here instead of the welds, and of course that means the block shear here may occur. Now that's pretty clear, right? And you have a bolt bearing tear out here, bearing tear out, and block shear, and then the rest should be the same. Okay, the bolt shear rupture on both sides. Please notice that if you have the bolted, it means that on this side, the beam side, you have say one set of bolts, but it's double shear because we have double angle. So it's double shear on this side, whereas when you go to the other side, you have two angles, right? So you have 6 bolts on the support, like that. So you have 6 bolts on the support, but 3 bolts on the beam side. But the 3 bolts on the beam side have double shear. So basically, they are equivalent. And that means we can just pass the bolted double angle right away, because it's pretty straightforward. And I think this is one of the easiest one that we can manage, and we can design very easily. And I think apart from a little bit difficulty in the erection process, it should be very, very okay. Okay, keep in mind that one problem that you may face is that when you use 2 angles like this, the weakest point. Actually, I prefer the word Achilles heel, but if you don't know the meaning, the history behind Achilles, and it would take me like 5 minutes to talk about Achilles and his heel. So, anyway, here the thickness of the web of the beam is generally very thin, and if we use double angle like this, you have 2 plates coming in here. So this will become your really, really weak spot. So when consider this, you need to be quite careful, because otherwise we're gonna end up having the shear capacity dictated by the very thin web of the beam. Okay. Now, next one, I don't have the picture for it, and I don't know why they have this picture. Every time I mention this, I have to say something like this. Anyway, this should be the called bolted, welded. So what happens with this one is this. When you're faced with a very, very thick support that you cannot punch a hole, for example, the column flange side. So what happens is that if this is a column flange with a very, very thick flange, we need to weld the angles to this first, because we cannot weld it. We cannot bolt it. So you weld it here like this, and that means we need to punch a hole here and then swing the beam onto the connection later and have our beam installed like that. So this comes later, and we still bolt on site, right? But instead the angles are now attached to the column first, and then you bring the beam in. That means the 2 angles are there already. We need to swing the beam in. That means we are required to make the room for the beam by cutting the bottom flange here. Otherwise, you cannot push the beam downward into the two angles. Okay, so we need to cut the bottom of the beam like that. Okay, and the US people will call this the knife connection. A knife connection. And when you have something like this, you see, for the beam, block shear now cannot occur. Because if the block shear is going to occur, it's going to shear off through the top flange. So when we have something like this, block shear is gone from the beam. And the cope strength here, the F critical is also gone. You need to check the cope strength still, but you don't need to check the F critical because this is the tension side of a simple beam. So it shall not buckle. Alright? So the cope strength here shall be Fy multiplied by S net right away. Okay? And now, yep, we still have bearing tear out in the beam web as usual. But for this, after you consider the big four of the angles, it's now time to consider the welds. And if I draw another picture, you should have the welds. And that's the thickness of another leg of the angle, right? We can have the welds on this side like this. And luckily, we have the formulas for it developed by some researcher somewhere, I don't remember. Here. The formulas for calculating the strength of the two welds here are as follow. And this is the stress, and from this, L is of course the length of the welds, and E is the eccentricity, which I forgot to draw on the pictures. I gotta go back. Here, the E should be this distance, right? Because we have the shear here. So the E is that one. And that becomes the L here. All right. So you can just use that formula, which has been developed based on the stress distribution of the well. And there you go. That's it. So now we can handle double angle connections with ease, right? All of them. Please notice that there is no welded, there's no welding on both sides, because that would mean you have to weld on the construction site. Okay, so generally you shouldn't do that. But then again, if the size of the work is small, that may happen, right? Okay, now we are going to have to deal with a single angle. This is the very, very popular one, at least in the US, and they say user-friendly, very, very easy to construct, and the erection process is also very, very easy. But the problem is the calculation is not so, because eccentricity is everywhere. Okay, and let's go here. This is the consideration of the eccentricity on the supporting member or on the, say, the primary beam. So that's the bolts on the support side. The eccentricity on these bolt group must be considered every time. You can have one column of bolts like that, and the eccentricity becomes the distance from the center line of the bolt to the center line of the force, which should be right at the center of the beam web. If you have two columns of bolts, again the eccentricity is from the center line, the centroid of the bolt group, to the beam center line where the force is, and the center line of the beam web. Okay, and when you have this eccentricity, you either have to go to the table and look at how many bolts are left for you to design to carry the shear after considering the effect of eccentricity, or we just use the classical method. Okay? And if the bolts are on the beam side or the supported side like this, if you have two columns of bolts, again you need to consider the eccentricity of the bolt group, and the E would start from the centroid of the bolt group again to the face of the angle. Okay, if you have one column, they say you need to consider eccentricity only when the distance from this center line to the face of the angle is greater than 3 inches or 7.5 inches. So, you know, the only one condition that you don't need to consider eccentricity. So for me, just consider it every case anyway, right? And notice that I don't include the welds here because if you use the welds, that means you already have to consider eccentricity for the welds, okay? By either using the classical method or tables if you have. One extra very unfriendly failure mode, not one extra, two extras actually, that come with the single angle is the flexural failure of the angle itself. Because you only have one angle, so it's pretty weak, we need to make sure that the angle does not fail under bending as well. And we have two things. First of all is just typical flexural yielding of the angle with the eccentricity. So this is pretty similar to, you know, when you consider the cope section, right? When we look at the angle, let's say on the yielding side, this becomes the section where the bending occurs, right? So when we calculate this, it's just basic my over I formula, okay? So the stress here will be equal to Fy multiplied by y over I, or elastic section modulus Sx, right? And that's x-axis. And S is, of course, if that's the T, the thickness, and if that's the length, L. The elastic section modulus of a rectangle is TL square over 6. I hope you can recall that now. BH square over 6, which comes from the TL cube over 12 divided by L over 2. Okay? Right? That's yielding, no problem, easy enough. But we have another mode that is rupture. This time they want us to investigate into the plastic behavior of the net section. Now, if you could recall what we had yesterday about plastic section modulus, you don't look very happy. The food must be good, right? So, yeah, the plastic section modulus is the sigma AIYI, remember? You sum the moment of the area to get the plastic section modulus. So that means if it is a net section, you need to start, you know, summing up the area that is remain after you deduct the holes, you know. So it looks like that maybe. So it's a net section, and let's say this is the centroid, where you have maybe the plastic neutral axis, which if it's symmetric, it should be the same at the same location as the elastic neutral axis. So the zx of this section will be the summation of this, you know, a multiplied by y, and then that area multiplied by y, and z would be again AIYI. That's how you can obtain the plastic section modulus of this net section. Okay? Be careful when you have one in the middle, because you need to break it into two pieces before you can use this, right? And okay, so that's it. The Zx as said in the slide. weird noise. And actually, I think if you want to have a good picture, or you think my drawings are good, you can just come take a photo here, right? I don't think anyone will hold the copyright of it because I don't mind. I draw it all the time. Okay, so that's it. That's a zx here. It's a summation of sigma ai yi. Okay, and another thing is that you need to consider bearing tear out by doing this. C is in fact the value of the number of effective bolts taken from the instantaneous center of rotation method. Because the way they handle this is that, let's say if you have 5 bolts, but you have the effect of eccentricity. So because of that, the number of effective bolts you have left for carrying the shear may be 3.6 bolts. It's 1.4 bolts are gone due to the eccentricity. That C becomes 3.6. 3.4, which one I use? Anyway, so you get the point. But if you don't have that table, I don't know. Is this the new suggestion for bearing tear out? They used to be just calculated right away, but now we need to find that C. Okay. And the value here is the bearing tear out of the outermost bolt, and then multiplied by the number of effective bolts. So let's hope that it should not govern if you don't have the means to calculate for it. And the next slide is just to show you the eccentricity distance that you should use when you consider the flexural strength of the angle from those 2 modes, okay, which is this one, the yielding and the rupture. You see, we have the eccentricity distance here, and generally you can look at this. It's a distance from the first column of the bolt to the fourth. That's all. Okay. Yeah, because I have the table, so the steel beams at my house are connected to the single angle connection. It works just fine. Anyway, the next one is the single plate. Well, this is a little bit more difficult, but it is very good in terms of construction and everything, because you just weld the plate to the support and then bolt the beam to it. Just one plate. So in terms of material, it is extremely safe, and it is the most popular one to be used with the moment connection. Okay, but the connection itself is a bit complicated because if you weld it here, how would your beam rotate? The rotation of the beam can only occur when the bolts can move through the plate itself. So there are some restrictions that follow because of that. And here are the conditions. Based on AISC 2010, I haven't seen the 2015 yet, because the details like this, as I told you before, are in the manual. They're not in the spec. Okay, so what I have here is based on the 2010 manual. But I don't think it should change much because I think most of them are based on the results that I got from my research. I like to think it that way because they look very, very similar. But anyway, no research has been done about this afterwards, so it shouldn't change. Anyway, back here, in order for us to have the conventional type is very easy to install. You need to satisfy these criteria. That is, the number of the bolts should be between 2 and 12. And whenever I see this, I should tell you that general requirement of the bolted connection anywhere, the tension, compression, axial force, or shear, or anything, you should not have bolts less than 2. With that said, you cannot use 1 bolt in the axial force connection, right? It's too dangerous. At least you should always have 2 bolts anywhere. Unless, of course, you want your connection to just rotate like a fan like that. That would be the special case. Maybe you would need that sometime in the future, but it's not recommended. Okay? So from here, we can use number of bolts from 2 to 12. So I can safely say that for our country, the largest H shape that we have is H900 by 300, right? And 900 cannot fit, more than like 8-9 bolts. So we're not going to exceed this number. So we are fine, okay? And the distance between from the well line to the bolt line, which they call the A distance, should not exceed 9 centimeters. So if we can satisfy this, you can have the conventional single plate connection, which the design is simple. That is, you only need to consider plate big 4 and the well rupture with eccentricity equal to A, and bolt shear rupture with eccentricity as listed here. That's it, very simple. But you need to satisfy this first, okay? So from time to time, you may find a case like this, which is very popular, but in terms of design, it means a headache. People prefer this. Right? If you have a beam, you can either cope the beam coming in like this, and then you have the plate here, right? Or you can just extend the plate out to catch the beam. But when this becomes the case, you will see that your A distance is very, very large. Right? Which one is easier to construct? It depends on many, many things. Oh, the plate should look like this, right? And then you weld it here. This would becomes difficult because, the extension is long and you tend to have a problem with the moment and eccentricity and everything. But if you use it like this, you need to cope the beam on both sides. And perhaps, the strength left here is not much. So, pick your problems, right? Which one you want to have the most? Oh, it's almost 1 o'clock. I need to hurry. Okay. Now we have only 30 slides left. And again, you need to satisfy the conditions of the plate thickness as well to ensure that you can have enough ductility and the beam can rotate, as this one. The next one is the seated connection. As we're just going to go through this because you can read it yourself. It's popular. It's very easy to construct. And I think it's one of the most popular one if you want to connect your beam to the column web side, right? This is the web of the column. So this is the most convenient one. The rest of the connections I mentioned before, it's very difficult to do on this column side, right? On the web side. And we have the unstiffened where you don't have stiffeners here. And you have the stiffen where the stiffener is added to strengthen the seated connection further. Now, funny how this picture is not quite right because the proper detail for the seated connection is that you need to cut this plate. Now I'm going to draw it on this. I found this picture from the internet and it's not quite right. Now, I don't believe this very much in the beginning when my advisor told me, but a few years ago, I went to Indonesia and I found the details that they use this the plate with the steel column, and they use a plate like this because generally I have been taught to use the plate like this. You need to cut this portion out. And I found a case where this portion wasn't cut. And you know what happened? It buckled. And and that's exactly what my advisor told me. It's gonna buckle. So, and when you did not cut this, and when you don't cut this, when the buckling occurs, it's gonna cause more, failure to this plate than just cutting it out. So the proper detail is just to cut it to prevent buckling. Because when it occurs, you're gonna feel sorry for yourself. Okay? So that one is not quite right. We need to cut it. Otherwise, this portion will just flip. Okay? All right. And again, that picture as well. That is not right. You need to have the triangle plate like that. That is right. So please do have the right detail before the buckling occurs. Okay, so now back to the slide. Okay, that's a gimmick. Just skip it. Now, generally, the idea to design the seated connection is that we will calculate how much distance we need here so that when you place the beam on top of the seat, these local failure will not occur. Right? Remember that these two failures are a function of this distance, the distance where you have it here when you place the beam onto the concentrated load, or when you have the concentrated load acting here. So the bigger this distance, the more your beam can resist these two failure modes. But I just found out myself that trying to prevent this sometimes is not really feasible, because I try to develop the typical details for steel structure, and then I found out that sometimes, because let me say this first. If we have these two failure, one way we can fight with this is just to add bearing stiffener to the beam, right? And sometimes I find that adding bearing stiffener to the beam is better than trying to have the big seat to support the beam so that these two failures do not occur. It just has to be very big seat so that these two failures will not occur. If you do not remember the formula, let me just go forward. Remember that? Oh, I forgot to change that. That's the N, which is I changed to LB yesterday, right? So this is the distance underneath the seat. The bigger this distance, the more the beam can resist the point load. But sometimes it gets so big that you rather have a stiffness. Okay? So if that's the case, if you have bearing stiffness, you don't have to design for anything except to make sure that your angle will not fail under bending. And the bending moment of the angle can be easily calculated, and the cross section is here. But remember, it's pretty thin. So this is unstiffened. When you add stiffener, you don't need to consider the bending of the seat itself. The eccentricity is equal to the clearance plus n over 2. The n again is the distance here. Let me draw a picture so that you have it better. I was thinking about not drawing it, but this is better. Say if this is a beam, and this is your seat. Now this distance is the N or LB yesterday, right? Whatever we want to call it. The bigger you have this, the more your beam can resist the reaction here. But sometimes it gets too big, you should have the bearing stiffener here to prevent those failures from point load instead, right? So you can have bearing stiffener as well. And you just need to make sure that the bending of the plate does not occur. The section of the seat that will resist the bending is this one, right? Because it's going to bend in this direction. So you know that you don't have the big section modulus because the depth is only the thickness of the angle or the thickness of this seat. So you don't have a large moment of inertia. That means this angle cannot carry a very heavy load. And of course, the distance behind the beam up to the face of the support, this is clearance. Okay? But that's it. So drawing some picture for fun. Please forgive me, this is already 1 p.m., so I'm just going to take a few more minutes to try to finish this off, right, before you guys have another session. Okay? And if it's a stiffened seated, it can carry much more load because we now have stiffener. So that means the shear force will be transferred from the beam web to the stiffener directly into the support. So with this detail, this seated connection can carry heavy load. If you don't have stiffeners, no, it can only carry maybe 15 tons, no more than that. But if you have it, that's fine. This is the same problem, but when you have stiffeners, you need to make sure that your stiffener is good enough by preventing the local buckling and by having a proper dimension. The last three, it's just sort of I'm not sure about it because I found these two possible suggestions on failure from the textbook, but it is Salmon and Johnson textbook, which is, you know, the monumental steel textbook, so you better believe them a little bit. Anyway, you need to also check the eccentricity of the weld if you want to weld the seat to the support. If you want to bolt the seat to the support, there's no eccentricity. Okay, and the eccentricity itself, it's equal to n/2 plus the clearance. Okay, we can forget about the column web failure because it's been proved that if you use the B distance less than this, we are safe. And the B distance can be seen in the next few slides, I believe. Yeah, that's a B. Okay. All right, let me go a little bit quickly. Now, if you want to design for these two local failure not to occur, these are the formulas, and we already mentioned that yesterday. And if you want to weld the unstiffened seated connection to the support, we have the formulas for you. So we can use that right away. This is from the research by a guy named Sputo. Okay, so we can use the formula right away. And if you want to weld the seated connection, we also have the formula in the next page, like that. Also from Sputo. And yes, sir, this is for the dimension. I never, you know, dive into this myself because I just found this from the Salmon and Johnson textbook not long ago. But again, when you have the stiffened seated connection, first of all, you need to make sure that the thickness of the stiffener is good enough. Now we have the ratio of the yield strength here because chances are you may use SM520 beam in the future, but the plate, it's always SM400 or SS400, right? And when you have the difference in strength, you need to make sure that you compare the strength as well. So that in that case, if you use SM520 beam and you use SS400 for the plate, the thickness of the stiffener should be thicker than the beam because of the ratio of the yield here, okay? And this is to make sure that your stiffener does not have local buckling problem. Remember the limit? 0.56 square root E over Fy, which is 16 for SS400. Okay? And that is your W, and that is your B. And if you want to check further, you know, bearing on contact area, you know, the bearing between the stiffener itself and the plate on top, right here in this area, is 1.8. See, you know, generally right now the specification says that the bearing strength is 1.8 Fy, but in terms of bearing tear out, it remains 2.4 Fu. Okay? So that is 1.8 Fy multiplied by the thickness of the stiffener and multiplied by W minus clearance, which becomes that distance. Okay? And bearing on eccentric loading, that's kind of crazy because they think you need to consider bending stress in this portion as well. And then if you have the welds, you need to consider the base metal. Okay? I think that's it for the shear connection. Any questions? Wow, it's already 1. I have a few minutes left to go through moment connection, so I shall be quick because the main concept for the moment connection is just that you can turn moment into the axial force, right? By using the couple concept. And when you have the moment into the couple, one is tension, one is compression, you just have the connection for the axial force and that's it. Simple enough. Okay, so because this is the introduction, so I shall be quick and just go through this. So that if you have to come across this in the future, you know what you need to do your further study, okay? Now here, of course, that's a gimmick, shear and moment, of course. Now, you can turn the moment into the axial tension and compression by dividing the moment arm, which is the distance between, tension and compression here. But one thing extra that you need to do is to check, because when you can turn moment into the axial force, it means that if that's your column, and that is perhaps your beam, your moment connection, if you can turn the moment into the axial force, it means that these couple will also act as point loads on the column as well. So you need to make sure that your column will not fail under these point loads. We call that column side limit state. Limit state, which is like, yielding, crippling, just like what we have with the beam before, but with a few additional extra. Okay? And still drawing that.